Testing, 1, 2, 3. So I've got another harmonic drive, pink motor from Germany. It's a CHA-32, and we're just going to take a quick peek at the winding information here. But let's look at the model number here on the motor. So zooming in, CHA-32A. That's the winding. 50 is a 50-to-1 gear. I'm not sure what the L stands for, but an M is for multi-turn, 1024. So this is a hyperface, and it's got sine cosine. And I think the B is for brake, because I had to add 24 volts to engage the brake so I could spin the motor. Let's take a look at the classic hyperface type of configuration. It's now part of CME version 8.1. It's been in there the whole time since 7.1, but now we just offer it up. This is not the DSL 2-wire that requires a transformer for voltage and data to be transmitted on the power lines. That's a future adapter from Copley, but there's some configuration, but we'll concentrate on the wiring first. This is sort of a classic drawing showing the outer shield connected to the encoder case, which then in turn is connected to the motor case, which is not necessarily a good idea, but that's just the way they do it in Europe, so it functions. That's what I did. And you can see there's a sine and a cosine and a data plus and minus. S and S not on most drives, but I'm using an AUV APV, and the data communicates bidirectional data in and out on the A and A naught, or the S and S naught if it's labeled as such. But the idea is you ask the encoder for the absolute position, and it tells you what its absolute position is, and it does it on power up or reset, and then we look at the sine cosine. And so with the sine cosine, we'll have to interpolate to get the right counts per rev. This sine cosine may be considered kind of incremental, but it's interpolated. And you notice the voltage is not 5 volt, it's 7 to 12 volts. So the signal ground is common to a little power supply. I used a 9 volt, 800 milliamp supply, or more than that. And this is this little regulator chip in here. It's like $8, and you hook up the 24 volts going in, and you get your 9 volts coming out. Actually, it says 11 to 32, and then you get 9 volts. 24 volts is typical in this system because there is a break. So just watch the wire colors here. Red is power going in, brown is power coming out, and black is ground. That's all well and good. And we'll take a quick peek at the cable for the motor. We see M1024 for multi-turn, S is for single turn. Same. We have power supply 7 to 12 volt as red, and then ground is black. These are fatter wires. There's another black for cosine. It's a smaller wire. It's actually a twisted pair with reference cosine brown. You got your sine yellow, your sine reference green, your data violet plus, and your data minus blue, and a motor temperature sensor, which I'm not using because I have current limit set to protect the motor. There's a shield. It's not shown here, and I have no idea what blue and yellow is for because they don't say. We splice back the cable a little bit. We see the outer braid. Actually, inside the twisted pairs for sine and cosine, there's another. I stripped it back further, and there's a shielded insulated cable for the sine and the cosine. So there's an inner shield along with the outer shield. And for testing purposes, I just connected the inner shield to the outer shield and connected it to frame ground, which goes to earth, and it works. But there's a better way to wire this, and I'll talk about that in a moment. But just note that the skinny black wire is a twisted pair with the brown, as opposed to the fat black wire, which goes with the fat red wire for power. That's the 7 to 12 volts. You could use 9. I use 12 or 11.8 on my little power supply. I'm not using the gray and the gray black or the black white for thermal sensor because I'm good to go. But you can see in this drive at AEV, the data is on blue and purple, A and A naught. Blue and purple is a twisted pair, and that's probably inner shield too. But the outer shield braid goes to frame ground, good path to earth. Signal ground, common between the power supply and the drive. So yes, you hook up the signal ground, and you do not hook up anything to the plus 5 volt output. Sine and cosine, green and yellow, cosine, brown and black, and this is purple or violet and blue. So that's a good diagram for wiring. Let's take a peek at the CME. It'll show us the, before that, look at the best way to wire. Just pretend like there's no clock here, just the data, bidirectional actually. So the outer braid shield goes to frame ground. There's an earth connected to the frame ground on the AEV easy board. You also connect earth to HV common so that when you deliver large power, it's referred to earth and your serial port doesn't blow up. But look at the inner shields here. So inner shielded, separately twisted shielded pairs go to the signal ground, right? Okay, so this has the most noise immunity, gives you good signal to noise ratio. You get the best count resolution, although it looks pretty good even if we go to the outer shield, and even if the shield is connected to the encoder case, which in turn is bolted to the motor. So the encoder is actually connected to the motor case, which is not a good idea. So you see here it's shown not connected. It'll probably work. It works for me. Good noise immunity though with a high voltage drive. So this might just be a little bit better. So let's move on to CME, and we'll look at the basic setup for this unique feedback device, Hyperface, brushless rotary motor. Yes, there's a brake. I applied 24 volts. I selected Hyperface from the list. It's not alphabetically sorted, but there it is. And it comes with analog sine cosine as part of the Hyperface, so you don't put it on the load unless you have a separate feedback device on the load. Let's take a look at the bits. It's single turn, 15 bits, 2 to the 15, 323, 768, right? So 12 turns, that's 4096 revolutions. The encoder sine cosine is 1024 line count. So that's for the sine or the cosine. And the count would interpolate, just square them up and you get 4096, so 4 times the line count. And then if I interpolate 8 times, we could interpolate a heck of a lot more if you want more resolution, but what's the point? It's at the motor shaft, not at the load. And you get absolute single or multi-turn on power up or reset, and it matches the counts per rev for the single turn, 32,768. It's good enough. Never ignore your feedback device. Fix your cabling, grounding, shielding problem. I guess if there's a bolt of lightning, you could ignore 3 in a row. So, but I never do that. I fix my cabling, grounding, shielding problem. If you have a brake, you can say, oh, it takes me a second to stop. I can turn the brake on when I'm going slow, maybe 1 RPM at the motor shaft. And the brake takes about 150 milliseconds to engage. I haven't tested this one. You can put in 200 if you want, but typically it goes click like a solenoid, which takes time. And then we can hold. So this is for like an emergency stop where you want to hold position, come to a controlled stop, hold position, and then turn the brake on and wait for the brake to turn on before you let go of the load. It's in a can open over EtherCAT mode, and that's fine. And you could emulate the motor feedback out. That's a lot of counts per rev. But we'll see from the motor data that we can't go very fast. So here's the motor data. Okay, so these units from the data sheet would be in volts RMS, 37, and Newton meters per amp RMS. And if you know the RMS current, you can multiply these two numbers and get this number. So let's take a quick peek at the motor specification. So here's the 37 volts per kRPM. Here's the 3.2 amps RMS multiplied by the square root of 2, and you get a slightly higher current. So I know the torque is more. It's okay to take the rated torque and divide it by the torque constant in Newton meters per amp RMS, but that's not including the inefficiency of the 50-to-1 gear, so you're kind of robbing yourself of a little bit of current. So you can see if I use these and press calculate, I should get on the iLoop screen 3.2 amps RMS times the square root of 2. So let's do that. 3.2 times the 1.414 equals 4.5 amps. So 4.5 amps. And 10 amps is fine. You probably get 2 or 3 times that for peak. But that's really what you can get out of this motor according to the amps RMS. I'm going to skip the flash. Good change. Quick little check on the manual phase. Oh, the motor doesn't turn. It's only 10% of the motor's current. Give it a good solid 3 amps. And now your phasing, when you go forward, counts must go up. You can see the currents UVW. And if your power up or reset phase is not proper, look, you got 120 degrees of offset. Fix that. Going forward, counts go up. Going reverse, counts go down. All's good. And then on power up or reset, you should see the same absolute position. This is the single turn. You could do it gives you multi-turn if you have multi-turns. But I just rewound the motor back to 0, and then you could attach it to the load. Note, it's a 50-to-1 gear, so you could use the wrap. So 32,768 times 50, 1,638, 400. Okay, close, save the flash. And now when you jog the motor at a good clip, you can see you'll get a single turn at the output. So it's multi-turn at the motor, but it's single turn wrapping at the output shaft. So there's a 0 position. You see it wrap. And then you could home and say, well, I don't like this position as my 0 position, so I'll do absolute active immediate home, and I'll put in minus 10.05017. I want this to be my 0 position, and then hit home, and it will automatically home on power up or reset. I save it, I exit, I look at the control panel, I'm referenced, that's my 0 position, I passed it, and try to get to 0. Oh, there's a wrap. There it is. There's right around there, 0. And on the scope, of course, you can monitor the sine and cosine as we're rotating, and that's always nice. So you can see the voltage sine and cosine, and you can see the position change over time. Oh, that's kind of fast for that. We'll go a little slower. So I'm using the scope at the maximum 25 milliseconds, and it's plus or minus half a volt or 1 volt peak to peak. And you can see the position change, and it keeps counting up, and then it'll wrap. I think that's good. I tune the velocity loop, watch the speed limit. Actually, the volts per kRPM is 37, but the volts peak to peak, not RMS, is 50. So I got 48 volts. So I'm not even going to go 1,000 RPM. So this 6,000 RPM is definitely like 240 volts AC rectified. And watch your limit here. You may want to increase this to faster than the rated speed or whatever your voltage can do. So again, we're not going to go over 1,000 RPM. I think I got up to 500 RPM with some peak currents because the winding resistance is 37 ohms. I measured it, and times 10 amps, that's 37 volts for peak current. So yeah, you need a higher voltage if you want to go faster or accelerate with higher torque, but you can spin it at 48 volts and it functions. But the AEV 18010 can do 150 volt DC bus 175 volts.